So, meine sehr geehrten Damen und Herren, ich habe die große Ehre und das Vergnügen, Sie zur Vorlesung von Professor Alexander Penn zu begrüßen, zur Antrittsvorlesung. Und wie Sie dem Programm entnommen haben, beginnen wir mit einem Grußwort von unserem Präsidenten, Professor Andreas Timm-Giel.
Yeah, I'm not that tall. Dear Professor Penn, lieber Herr Kollege, dear Alex, dear friends and supporters of Hamburg University of Technology, dear ladies and gentlemen, I hope I've addressed everybody. Inaugural lectures, there's something very special. It's a very special moment. It's a great joy for us. It's something like gives us an opportunity to proudly present our new staff members, even if that's one year or 2 years ago, and give them the opportunity to introduce himself or herself. In this case, it is the Professorship for Process Imaging, which we have filled with an excellent candidate, Alexander Penn, already mentioned. I won't go into much details about his person. I will leave that to other than just say it's a great colleague and an honor, and we are happy to have you with us. As a president, I want to go maybe on the storyline, on the history, how this professorship came along, because it is not a replacement of just a retired professor, it is a new professorship. And that is a result of the growth concept, the growth strategy, the growth phase, which we have gone through from 2018 to 2022. Basically, we started in the discussion, how can we developed the university further in 2016 and got the grant, the funding for it. And then we have had basically in total 15 new professors. Of course, we also had some other constraints. But in developing this university further, we had something like a process before. We identified the strengths and the weaknesses and opportunities of our university. And one of the things which also led to the selection of professorships which we wanted to fill was something like the interdisciplinary collaboration which we have, which is a crucial topic for us, and also interdisciplinary, also combined with digitalization. That was one part. And the other part was we wanted to strengthen the fundamental research. We wanted to strengthen the complete chain from fundamental research to application. And that you can only do by stärken, as you would say in German, or by building on existing excellence and strengths. And at that time, we basically had a lot of proposals, and the School of Process Engineering addressed us as the presidential board and said, well, we have an idea. And process engineering at that time and today is one of is probably the one which had the most potential. Now it's the expertise, but at that time it was the most potential to go for something great. And something great is greater projects which have an impact. And they came with a proposal of saying, we want to have a collaborative research center, an SFB from German Research Foundation, which is one of the big things you can do. And the idea was to have a new generation of reactors, a smart reactor. And for that, there was a really good argument on that. We need to have a professorship on process imaging. If I think about what a smart reactor is, and we had a lot of discussions with that, and I'm an electrical engineer, and I do telecommunications, so that's really different. But I can try to explain smart to you now. Smart means, smart is for me smart devices which communicate, but that's not the idea here. They basically say it's a self-adaptive controlled reactor, so S we have. It's something like autonomous controlling itself, the A. It's resilient, R. And it's something transferable to various products and scales and sites and locations. That's the M. I missed the T. I missed the M, which is there for multi-material and systems we can use. Reactors, so that we have the smart together. Reactors, there was a nice story which Michael Schlüter gave to me, and I really liked it. He was basically showing a tube, and that was a reactor in 1900. And he showed a tube of a reactor in 2020, which is more or less the same. So nothing has really changed much, and you want to make it better. You want to have it for the future. You want to have it for bio-based resources, which have different quality. You don't start something and runs forever, but it changes the incoming process or the incoming materials, and materials basically change. So we were more or less convinced, and then we were saying, well, we don't only need people or engineers who can control the process or can engineer the process, we also need someone who monitors it. And that's, of course, very clear. If you want to look into science, you have something like the modeling, you have something like the creative ideas, and it all has to be based on the reality, which means you have to monitor, to do experiments and see. And that was the idea. So that was good. So we basically said that's one of the 15, and we advertised this position. And the professors of process engineering basically went further, and they basically applied for state research funding, for research fund at our university, which was also part of the growth concept, an iCube lab which we had. And in 2020, Alexander Penn already came. And then in 2020, we also changed the board of the university. I was becoming president. Professor Smirnova was taking over as vice president research, and we basically changed a lot of things. And we also changed the research structure of our university. So we basically had the idea what happens with the growth concept. On the other side, we had to cut down in the basic funding of our university because we didn't get all the salary increases refunded. So we had to think about how do we want to form? What is the if you look from outside the university, what are we standing for? And we defined 5 research fields. And one research field is advanced material and bioprocesses. That's something which you perfectly meet too. And that was only because we had the strength already. There was a CRC in material science already. We had the idea with state funding and the iCube lab that this could become the next CRC at that time. So that is one of the big fields for our university. Also nice in cooperation with the others. And the other are more Hamburg topics. Hamburg topics you can think about is aviation and maritime technologies. It is something like energy and environmental systems, clear northern Germany. It's logistics, mobility, and infrastructure, and the cyber, physical, and medical system. The last, and also in cooperation with the University Hospital in Eppendorf. So, in the field, in the field of advanced material and bioprocess, the major equipment which we have, das DFG Großgerät, which is there, that's your MRT. That I think we hear a lot. I heard it's something like it's the largest in the world for this purpose, and it will be probably topic of your lecture as well. Imaging techniques is something which is pretty important. I already mentioned that you need to observe and monitor an experiment. You need to have an understanding. And in process engineering, it's even more important, and it allows us to have a deeper physical understanding of the processes in time, in high resolution in time, as well in space. And I think that is something which really will allow us to have more and more advanced material and better processes, optimize them to be more energy and resource efficient. Then maybe important for us and for you as well, 1 year ago, it was more or less this time we had a final evaluation of the proposal for the CRC. And that was something really big, very nice, organized, and you were a full member of it. That is really good. And in the end, in May, the decision from the German Research Fund came that we got the CRC granted. And that was is led by Michael Schlüter and Irina Smirnova here, both of them. And I think we all participated, even the presidential, also the university board, as well as you, Alexander, as part of that. We were basically celebrating, wir sind SFB, we are SFB, and that is a great thing. Why do I emphasize the CRC and that much? It's just a project. Well, it's a 60 million euro project, and you get something like 4 million per year. But it's distributed to 10 professors, so maybe is that something big? It is something big because in this, and that was also one of the evaluators was saying, that this is a milestone in reactor development, and it's something you can work together with something like 15 PhD students at the same time, with 10 professors, 12 professors at the same time, and work on a topic. And you have the interdisciplinary exchange, you have international collaborations. It's something big, and that is really interesting. I used to work in one many years ago, and that was something which is something so enlightening. So I'm really happy, and a bit jealous that you are in this team. And then you can say CRCs are not so many. So Hamburg University of Technology has 2. That's something we say if you have something 100 million euros basic funding, so 50 million per CRC. Technical University of München has, I think, 10, something like this, and a basic funding of 750 million euros. So one SFB in Munich is something 75 million euros, in Hamburg is only 50. And if you go for the state of Mecklenburg-Vorpommern, they have 2 in the complete state, as many as we have as a Hamburg University of Technology. So they see that this is something which we can be and we are very proud of. Okay, let's go a bit back to Alexander Penn. You're a crucial element of the SFB, but not just your MRT is part which is important for us. It's also you as a scientist and as an esteemed and very much liked colleague. And you were, and that's why we have now a few days ago since you were appointed, but you're fully integrated from day one into Hamburg University of Technology. And you took roles and responsibilities as we can just wish as a presidential board, and you're even now the dean of the School of Process Engineering, and that's an exciting development. We'll see much more of you in the next years. And so, again, a warm welcome to you, dear Alex. We are very excited about what you are going to present to us now. And I hand over back to Raimund Horn, I guess. Yeah? Thank you very much.
Yeah, thank you, Andreas, for putting the numbers in the right perspective. And I would like to continue with a short laudatio. Dear Alexander, dear Professor Timm-Giel as our president of TUHH, dear Professor Irina Smenova as our vice president for research, dear Professor Wolfgang Kersten, our vice president for education, dear colleagues, dear co-workers, dear students, dear guests. Normally it would be the job of the dean of the School of Process Engineering to introduce our speaker, Alexander Penn, today, and also to give a laudatio to open this inaugural lecture, but that would be a bit strange because Alexander Penn, as we heard, is currently the managing dean. So for this reason, it is my honor to do this. I'm the vice dean, and I was also the head of the appointment committee who appointed Alexander Penn as professor at TUHH. And for this reason, it's a double joy and honor for me to do this this afternoon. And before I explain how it came about that Alex Penn was appointed professor and head of the Institute of Process Imaging here at TUHH, let me familiarize all of you with some stations in his CV. So Alex Penn was born in the beautiful city of Bozen in Italy, and he studied technical physics at Vienna University. And during his time as a student, he already went abroad to Spain for 1 semester as an Erasmus student that he spent at the Universidad Autónoma de Madrid. And after his graduation at Vienna, he joined ETH Zurich as a PhD student in the group of Professor Klaas Prüssmann, who is also here tonight. Welcome, Professor Prüssmann. It's a great honor to have you here. And co-advisor at ETH Zurich was Professor Christoph Müller. So after finishing his PhD in 2018, Alex stayed as a postdoctoral researcher at ETH and worked on new methods in the real-time monitoring of multi-phase and reactive flows with MRI. And also during this time, he went abroad, for example, to the US, to Columbia University, where he worked in the group of Chris Boyce on MRI problems. And he also spent some time at Osaka University in Japan with Professor Takuya Tsuji, working again on MRI problems. And then in 2020, Alex Penn was appointed professor at TUHH, which happened right to be in the Corona time, so not the most fortunate time to start, but he managed very well. So now let me say a few words how we attracted such a young, highly talented researcher in MRI to TUHH. I personally got to know Alex Penn at the annual meeting on reaction engineering at Würzburg here in Germany in 2018. And Alex Penn was giving a talk on the application of MRI to study process engineering equipment. And I was deeply impressed both by the options that MRI offers to learn something about reactive flows and transport processes in reactors, but also by Alex Penn as a speaker. And after the conference, I talked in the coffee break to Michael Schlüter. Where's Michael? Oh, there he is. Yeah. And I said, this is a technique that we could put to good use here at TUHH. But this requires two things. First, we have to be able to pay for such an expensive MRI scanner, which is more than €1 million. And secondly, we need someone who is able to operate it, because none of us was, and it's the same like buying the most expensive grand piano from Steinway. If you put someone on who cannot play, it will sound terrible. So that was the situation, but Michael Schlüter was also very keen to bring MRI to TUHH, because he knew from his colleague in multi-phase flow, Professor Dieter Mewes, who is sitting right next to him, and who is Professor Emeritus from Leibniz University, Hannover, how powerful MRI is to image liquid gas flow systems. So also welcome Professor Mewes tonight, and we thank you for stimulating this development. So after we knew we want to go for MRI, Michael Schlüter and the colleagues from the process engineering department sat down and wrote a major equipment grant, or in German called Großgeräteantrag. And we asked for such an MRI scanner. And this was a challenge because, first of all, this machine is rather expensive, as I said already. And secondly, none of us really had an expertise in this technique. But we promised in the proposal that if we would get funded, we would fund a new institute of process imaging, and we would appoint really an expert in the field. And this is what happened. We got the money, and we then started. We opened the position and scouted for a new person that we could appoint as a professor. And we had quite a number of applicants. But I think I don't tell any secrets when I say that really Alex Penn stood out in this application interviews. He not only had demonstrated a great research expertise in MRI, but he also had a very convincing research concept, what he wanted to do here at TUHH. And he also excelled in the demonstration lecture. We asked as a task to explain how you can measure a flow velocity with MRI. And all the applicants showed some things, some more mathematical, some more graphical, but Alex really showed it extremely clearly, and at the end, everyone in the committee understood how to measure flow velocity with MRI. So it was clear, and we made this decision unisono that we would put him first on the list. And fortunately for us, Alex accepted the position and moved with his family to Hamburg. And I can say he hit the ground running and immediately took over the purchase process of the new MRI, which we will see tonight in the lab tour. And in parallel to setting up his institute, which is hard enough because it's a new institute, he was an integral part in preparing the CRC application smart reactors that was mentioned by our president already. He redesigned the teaching module measurement technology for chemical and bioprocess engineering in our bachelor program and created a new module process imaging in our master program. And he also became the TUHH research coordinator in the European Consortium of Innovative Universities, short ECIU. And since 2023, he serves as the Dean for the School of Process Engineering. And in summary, I can say that with Alexander Penn, we appointed not only a brilliant and highly motivated scientist, but also a very likable and sympathetic colleague whom we all like to work with very much. We are very happy that you are here, and we are looking forward to many great things to come and many great results from the MRI scanner. And with this being said, I would like to close my laudatio and hand over to Alexander Penn now for the inaugural lecture. Thank you very much. Alex, the floor is yours.
Yeah, thank you very much for both the opening words, Andreas, very, very kind opening words, and also to you, Raimund, for these very kind Laudatio, the introduction words. I'm extremely honored and pleased to be here tonight, and it's fantastic to see so many people here, familiar faces that I've came across during the past years. So it was mentioned that this is a bit late for an inaugural lecture, but yeah, there was COVID, and I think and now we have the system running the MRI, so I think it's the right time, and better late than never, and I hope I can show you tonight what the MRI looks like, and what I will be doing here. And thanks to all my colleagues from the School of Process Engineering, to all colleagues here for coming, and also for a lot of people in the MRI community from in the north of Germany came here. So I'm glad to have people over from Bremen, as I see them here, Jörg Thöming and colleagues, from Rostock, from Magdeburg, from Kiel, and last but not least, my former colleagues from ETH, whom we spent the whole afternoon with, and we still optimized a few things at the scanner. Thanks for taking the journey to come here and to be here with us tonight. It's a great honor. And my parents are also here, so thank you very much. All right. My talk is about magnetic resonance imaging in chemical and bioprocess engineering. So I'm aware that not all of you are familiar with both topics, so my goal is to give you a brief overview of why we need MRI in chemical and bioprocess engineering, and what the current challenges are in chemical and bioprocess engineering. So chemical and bioprocess engineering, or bioengineering, does basically one thing, or does many things, but you can boil it down to converting raw materials and energy into useful products of our life. And raw materials are agricultural crops, ores, energy carriers, and the products are liquids, beverages, drinks, or pharmaceuticals. The COVID vaccine is a great example of bioengineering that saved a lot of lives on Earth. And also other products like garments, fuels, paints. So our modern life really relies on chemical and bioprocess engineering. But we do face a couple of challenges, and I want to specifically mention two of those. So one is the things here down in the corner. So we heavily rely in chemical engineering, on fossil raw materials and energy carriers to produce the things that we do. And what are these fossil carriers? Well, that's nothing else with a grain of salt. That's dinosaurs and what they ate many million years ago. And we're digging that out and we're burning it. And what we do is we release the hydrocarbons, so the carbon in these hydrocarbon bonds, and that goes to our atmosphere. And I think I don't have to explain you what that does to our climate. This was predicted 100 years ago by Arrhenius, a chemical engineer. And it turned out to be very true. So there is a strong correlation between atmospheric CO2 and global temperatures. And they tend to rise, and this is a huge problem that we will all face during our lifetime. So we need to get ourselves independent from these fossil material and energy carriers. And a second problem is the products, more or less, on the other side. At the end of their life, what happens with these? So in Western Europe and in many parts of the world, we do have a strong history of waste incineration. So we just burn our waste, and that just releases again CO2. But there's a lot of valuable materials in this that we could reuse. But even worse, in other parts of the world, landfills are very common, and plastic products pollute our oceans. Microplastics has been shown to be in human bodies. So this is two major challenges that chemical and bioprocess engineering face at the moment. And so one goal would be, or the goal would be to close this loop. So from going from linear production, so taking something and transforming it into something useful, but closing the loop and going from renewable raw materials and energy into sustainable products that can later then be reused as material streams, as inputs for processes. And yeah, for example, biomass or CO2 that we capture from the atmosphere as carbons in our materials. We do need the sea. That's in our products a lot, so we need to get it from somewhere, but we can get it from the atmosphere. Energy, there's a lot of energy coming from the sun and secondary from the wind. We just need to harvest it. And this is, yeah, political decisions, but also technical. And we're working here on the technical solutions. And also, yeah, have sustainable products, replace fuels as much as possible. Probably in aviation, this won't be possible, that when we can have synthetic fuels, but also plastics that dissolve after a certain time, and it's not that severe if they end up being in the atmosphere. And what's at the core of such, of this development? Well, you see, in such a plant, as a chemical plant, the core and the heart of these plants are reactors. We heard the term smart reactors a lot, but reactors, and this is indeed a picture taken out of the grant proposal that we were granted ago. And so the core of it is optimizing these reactors, making these reactors fit to adapt to varying qualities of raw materials, make them ready to produce different materials that, and do that fast. And what we need for that is a detailed understanding and knowledge about the processes happening inside these reactors. And what can possibly happen in there? Well, we have different raw materials, they mix, and we need to get them in contact. So where are which materials, where are the phases? So for example, liquid phase, solid phase, gas phase. Measure where they are in space and time is important. Measuring the flow of materials, for example, flow is really important when it comes to mixing and residence times. Temperatures are super important because chemical reactions, and we look at chemical reactions mainly, they do depend a lot on temperature, and if something's hot, it might react faster, and if something's colder, then it's slower. And ultimately, and this is kind of the holy grail in process imaging, we want to see where chemical reactions really happen. So differentiate between chemical species and really map in space and time where such a chemical reaction happens. And for example, why this is important in a bubbling fluidized bed, for example, that's a reactor type used for example, coating of materials or absorption of CO2 and combustion of fuels. And for example, here gases bubble through a granular material, so grains. And so it looks like a boiling liquid, so gas bubbles erupt, and they do behave in quite interesting ways. But the gas bubbles are very important to promote heat and mass transfer and mixing. And efficient reactor design and control really relies on the information of understanding these gas bubble dynamics. And so we need here 3D imaging with high spatial and temporal resolution. A second example that I want to give is temperature. So why do we need temperature? For example, in heterogeneous catalysis, like our colleague Raimund is investigating, we have a gas phase, for example, that passes through a packing of catalyst particles, and these catalyze a gas phase reaction. And when these are in contact, and then for example, this reaction is exothermic, we might end up having hot spots where we can locally exceed temperatures that are healthy for the catalyst, so they get degraded or deteriorated. Or we can also have cold spots, regions where we don't have enough flow, and then the reaction dies off, and then we have ineffective zones that then decrease the efficiency of the overall process. So thermal monitoring is very important in optimizing such reactors, and both in space and in time. So not only sticking a probe into a reactor and saying, well, the temperature at this one location is X, but really seeing the temperature map, so the three-dimensional distribution. That's a different quality of information. And also, if you compare it to numerical modeling, and numerical modeling plays an important role in the future of chemical engineering, then these really reliable and highly spatially and temporally resolved information are essential. And where do we get this information from? Well, there's a technique that you might be familiar with because you have had your own medical experience. When you had a broken ligament or something in your knee or in your ankle, you might have been inside such an MRI scanner. It's very loud, but it gives fantastic information about the interior of your body without cutting you open. And this is very valuable because cutting open, this is my skull, so cutting it open I would not have agreed. But in this case, it was just half an hour of loud environment, and then you can beautifully see how such a brain is made up. This is work by a former colleague in Zurich, where you can measure the instantaneous flow of blood inside a living human subject, in this case an aortic bow. And you can really see if something's dilated, if you have turbulences that make the performance of a heart weaker. So for diagnostic reasons, this will become useful in the future. This is also a technique. It's called temperature sensing with MRI, where a dog with a tumor was treated with thermally, so with a laser. The tumor was ablated, and with MRI thermometry, it was controlled if the temperature doesn't rise, because you don't want to let healthy tissue die off. So you really want to concentrate it to the tumor spot. And this is a technique that was used for this. And spectroscopy, so MRI, is a spectroscopic technique. It also contains information about molecules. So different molecules have different chemical magnetic fields that they see. So if there is an O, so oxygen in the vicinity, the field is shifted. If there is a C in the vicinity, then it's different. So that way you can tell a lot what different neurotransmitters, for example, are in this tumor here in the brain, and that might is useful for medical diagnostics. So we see that a lot of what we wanted from our reactors is already there, right? And it's no wonder. The body is nothing else than a very complex biochemical reactor, right? We eat and we drink, we also extract waste products, but we do have we think, and all of these things, they're massively complex, but in the end, it's very similar to a biochemical fermenter, for example, for the production of the COVID-19 vaccine. So the big challenge now here is, how do we take the clinical MRI technology, which is really advanced, as we have seen, so really big amounts of money have gone into this development during the past decades, because it's such a useful tool, and how we can translate them into process engineering and make them useful for what we want, really understanding reactors. And so it's, clinical MRI technology is really optimized for the human body. And that means the hardware is optimized for patients that lie horizontally when they're being scanned, so they don't move. That's important, that they don't move. And the materials, so the materials of human tissue, these scanners are optimized to, and the pulse sequences as well. And so when I started my PhD in 2013 with Klaus Prüßmann, and Christoph Müller, we set out to really modify all of what the MRI experiment is, and try to optimize it for this type of systems that chemical engineering has. And that entails dedicated MRI hardware. So really going close to the geometry of reactors. So in this case, a vertical geometry where you really have a proximity of your coils, because the signal decays quadratically in time. So you want to be close, and you want to have multiple channels to be fast in scanning. So materials manufacturing. So oftentimes it's even easier in chemical engineering than it is in the human body, because in chemical engineering, in a reactor with gas and liquid, you don't care if you add a little bit of poisonous contrast agents, whereas in the human body, you're quite limited on how much contrast agent you can inject. So this is even a part that gives us more freedom. But yeah, in this case, for granular materials, for these fluidized beds that I showed you, and I will show you in a second some more, it was important to synthesize particles that have strong MRI signals, so liquids encapsulated in polymer shells. Pulse sequences, so this is also a major thing that where you have a lot of potential to increase spatial and temporal resolution, is by sampling your data space in an efficient way. And for that, you need to do your homework here and have enough signal, because during the time you read out your signal, it decays. So if it doesn't deliver enough signal, or your coils are not there, then you won't be able to do these single shot excitation, time-efficient readouts. And yeah, of course, you need to reconstruct this data into images and to automate and process these and do image analysis and interpret this data. So as I told you, this reactor, for example, was modeled and then built. Previously, people used agricultural seeds like poppy and mustard seeds, but we came up with different materials that give quite a bit more signal, and we're further developing them and making them consist of contrast agents. As I said, these a little bit not so, it's rare earth dopants that increase the magnetic susceptibility, which improve homogeneity of the field and then give you even more performance. And yeah, if you compare them mechanically, this is much better. They're more spherical, so you compare them better to, for example, CFD simulations. They have higher proton density, so there's more oil in those than there is in those. And the signal lifetime, this is most importantly, as I told you, the signal lifetime really determines what type of sequences you can run, and this is important. For example, fast low-angle shot or gradient echo sequences, where you excite each line, they need more time. And if you can run through K-space, that's the data space in MRI at once, then you're faster. Or spirals are even better. For that, you need even more precise field control. So, in essence, we looked at the toolbox of the MRI chain and tried to modify and optimize each bit and stitch it together. And then, indeed, we were able to get down to 7 milliseconds per slice images. And I will show you afterwards also a video of, for example, this bubbling fluidized bed. And that gave us unprecedented information of what's happening in such a reactor. And so such an experiment looks like this. We have this reactor model. This was still done on a horizontal scanner back in Zurich, and with our coil. So it bubbles. I told you it's like a boiling liquid, and you can see it indeed is, but you have no chance of seeing what's happening inside. And with MRI, you can see that, what's happening inside is it's quite chaotic. And if you analyze this data set, for example, you can deduct many useful things. For example, how do bubbles interact with each other? How do they coalesce? How do they split? What's their speed? What's their spatial distribution in time? So they tend to grow. This is something known. But how they really distribute and how they interact is something that is, that is difficult to obtain without any other technique. But MRI, so far we were at the spatial distribution of phases. It can do that quite well. But MRI is super flexible as well. It can give you information about, for example, flow. And people have done this. And for example, this is work by Daniel Holland from Cambridge University, where they used quantifying flow with MRI. And it took about 20 minutes average of such a fluidized bed to detect the flow pattern. And by combining our fast imaging techniques with these phase-sensitive phase encoding, then we were able to get this down to 21 milliseconds per shot. So indeed, that was about 10,000 times faster and really opens up a different window of analyzing such systems. So sorry, it's a double microphone. I don't want. And yeah, we use this technique to study, for example, to quantify bubbling hydrodynamics in bubbling fluidized beds with different particle types, different fill heights, different fluidization velocities, and really try to widen our parameter space to get a lot of information out of the systems. We added small amounts of liquids. For example, this is also fluidized beds are often used for drying purposes as well. And if something's wet, you know that from building sandcastles on the beach, right? Wet sand behaves completely different from dry sand, so you cannot build a sandcastle out of a dry sand. On the other hand, you cannot fluidize wet sand, but somewhere in between, if you add small amounts of liquids, it starts getting into this nasty regime. And yeah, knowing more about this is possible with MRI in this case. And then also fluidized beds with internals. So for example, when you want to introduce or extract heat, you have heat exchanger pipes or baffles that do change the flow structure here, for example, to reduce the maximum bubble size. You can enter these baffles. And this was work already done by Hannah Rennebaum, who's sitting here. We measured in Zurich, so thanks for giving us the opportunity to come back to Zurich and use the scanner while we were here building our kitchen, so to say. That was very valuable, so we could use the time here to continue being productive. And it doesn't only work for granular materials, for fluidized beds. MRI works very well on liquids. For example, here, if a gas bubble rises in a column of liquid, we can nicely track its motion. We can nicely track the flow field of the liquid around this gas bubble. So it's something that is very useful for multi-phase reactors that include liquids. Now I had phase distributions and flow, and now we're going into the thermometry, so temperature. So temperature, there's various things you can do to measure temperature with MRI. One way is to look at the thermally, proton resonance frequency shift that depends on temperature in some materials. For example, in water, you shift this peak position in the NMR spectrum, and this shift here in parts per billion, so note this is quite a small shift, but it's a spectroscopic technique. You can really, really accurately determine this shift. That varies more or less linearly. It's not perfectly linear, you could probably do better, but in our first approach, we assumed it's just a linear slope, and this was work done by my postdoc Raquel Zayal sitting here, and also in collaboration with ETH Zurich. So we had a packing of spheres that we injected hot air. So this was initially at room temperature. The spheres were filled with water. You can see them here. And then everything was scanned inside a clinical MRI system, and we were able to track or measure the heating up of this packing as a function of space and time. So this was a full 3D sampled. So we did multiple slices. I'm just showing the central slice here, but it's a 3D measurement. And we did also some numerical simulations that back up our experiments. So it's something that it was a first of proof of concept of proton resonance frequency shift in fixed beds, and it's something that might become quite useful in the future. And for our projects, we are already very keen. And the last but not least ingredient that I promised is chemical contrast. So we want to discriminate between different raw materials, between different products in our reactor. And as MRI offers also quite a few options to do this. And for example, chemically selective imaging, where you look at different portions. For example, here we have a phantom. This is also a collaboration ongoing within the smart reactors with Tobias Knopp. We're working on chemically selective MRI. So if you look at a sample that's made out of water and acetone in two different separated containers so they cannot mix, then take an image and look at the spectrum in each pixel. It is different because water and acetone have a different chemical shift. And so if you only integrate over the water region and reconstruct an image, then that's what you end up with. And if you only integrate over the acetone portion of the spectrum, you end up with this inner circle. So this is one way of getting chemically selective contrast. Another way is to look at different relaxation times, for example, T2. For example, in this autocatalytic reaction where a cobalt-2 species reacts into a cobalt-3 species, and the catalyst is produced during the reaction, so it's autocatalytic, and there's like a wave front that propagates through such a reactor, and you can the raw material and the product have different relaxation times. And if you make your contrast sensitive to this relaxation time, you can track this reaction over time. And we showed that using acceleration techniques, we can still see this contrast very well, but speed it up quite a bit. So this is in general, in medical MRI, people are hunting for the next 5% or 2% because there's so many people working on the field here. This field is much more relaxed because there's very, very few groups in the world actually doing this, and a factor of 5 or 10 or 10,000. So that's it's just quite comfortable to work in a field where there's not so many competitors, so to say. And we're very much looking forward to establishing this technique within the CRC. I would briefly also mention work that we did during the past 3 years while we did not have a scanner running. So that was, we simulated CFD DEM simulations and compared it with our MRI results. And normally people just compare this instantaneous CFD simulations, numerical simulations, and the MRI experiments, but they neglect some effects of the MRI. So we used the CFD as an input for MRI simulations and simulated the experiment and looked what came out of it, and looked at different ways of interpreting, of comparing the two. And we got really interesting results, and that was just published. It was together with Chris Boyce at Columbia University and led by Stefan Bendos, my senior engineer, who's sitting right over there. All right. To conclude this section, I hope I could show you that MRI is indeed a very, very suitable tool for for chemical engineering, and it can deliver the spatial distribution of phases in different material systems. It can measure the flow. It can even map temperatures and chemical reactions. We do have some opportunities. This is more experimental yet, but it will become useful in the future. And it was already mentioned, we do have an MRI here that we will look at in a couple of minutes, and I'm really looking forward to showing you this system. Why did we go for something prototype-ish? Why wouldn't you just buy a machine? Well, the idea was, what's on the market is either micro-imaging systems. You might know the NMR spectrometers from Bruker or Varian in previous days. That's what they have fantastic spectral resolution because they're made for chemists. They want to discriminate between molecules, but they're very limited in the sample size they can take. And on the other hand, we have clinical systems. We can lie in them. We fit in those, but the height is quite limited. And process engineering lives from gravitational instabilities, so from gas wanting to go up and heavy things wanting to go down to have mixing. So most of the reactors are vertical and upright. And so I thought, and this was a discussion with people, if we could have the ideal system for process MRI, how would it look like? Well, we just take a clinical system and put it upright and tilt it on its side. And when talking to Philips, and I'm really happy to see so many faces from both the Philips Hamburg lab here and also from Philips Best in Netherlands. So it's a great honor. When I talked to them and said, hey, let's just take one of your systems and flip it up, right? And they were not so happy with that idea because, it floats in liquid helium and it's mechanically super sensitive, and if you turn this around, it will just crash and collapse. So we would have to re-engineer the whole thing, and that's millions and millions. We couldn't afford that. So we were really looking. So as I told you, these reactors are upright. We were looking for partners to build us such a magnet, and you don't only need the magnet because an MRI consists of a big magnet that creates a strong magnetic field, but also gradient coils that create spatially varying fields, and RF coils. So that was, and as well, and that's why Philips is here. You also need all the back end that kind of powers the system. So the amplifiers, the spectrometers, the cooling, all the infrastructure that is there, the computers. So we found a consortium of two companies. One is Tesla, UK, and Tesla Dynamic Coils. It's a daughter company of them. They said, yes, we will do it. We will build the magnet for you. It's a little bit smaller than a clinical system, but almost the size of a clinical system. And Philips agreed to deliver the backend. And we were very happy because also in Zurich, I was working with Philips backends, and I know them, and they work well. 3 years later, we now have this system here finally commissioned and working. We did some scans. I will show you one image that we took yesterday night. Stefan took yesterday, and I'm excited. This is the RF coil. So you see it's concentrically. This is the magnet, 4 meters height. So the magnet's mounted in a big hall of 7 meters at 4 meters height. And in the center, this is the open bore. There's the gradient coil, and inside is the RF coil. And a few specifications. I want to mention that this, and it was mentioned before, this was kindly applied for this funding was applied by my colleagues, Michael Schlüter, mainly, and Raimund Horn, and many other colleagues from the School of Process Engineering who also delivered their applications. And I can imagine that it was not so easy for you, not being MRI experts, to anticipate what you can do with this device. But it was convincing, and we got the money, and TUHH, agreed to chip in the second part of the money. That was also, thank you for that as well. And thank you for leaving me the chance to really do something out of the box, because yeah, I can imagine if you hire somebody and that says, yeah, I don't want to buy something, but I want to do it myself. But there's some risk associated with that, and I'm really grateful to you that you took this risk and you let us do. And I hope that I'm sure we won't dilute your expectations. So here are a couple of specs. I can tell you what probably more than at the MRI system. And this is a short video that shows the system in action by our two PhD students. And that is a movie made for the smart reactors. So here we see a fluidized bed that's being inserted into this MRI, and it's being scanned, and yeah, so there are still some phantoms, but yeah, the idea is that we now have the opportunity not only look at systems that are this size, because they were lying in, but several meters tall and even larger, and that is just a different game, and it's just a different thing. And what do we want to do with this? We have 1,000 ideas, and I'm very grateful to my colleagues for all their ideas, because they want to use this machine and they have high expectations. For example, I just want to mention a few. I cannot mention them all. This is a project that we have together with my dear friend and colleague Stefan Heinrich, who's sitting here in the second row, from the Institute of Solid Process Engineering, where we look at vibrated fluidized beds. You see this electrodynamic shaker, 150 kilograms of magnetic material right under the magnet, but we were outside of the 5 Gauss line, so don't worry. And we're also outside of the RF cage, so that's also something that was suggested by so this gives us a lot of flexibility to have here reactors. And the idea here is to compare numerical simulations and experiments and to predict how vibrations affect fluidization hydrodynamics. And in the course of this project, we're also using high-speed camera technology. For example, here we do have a first video of glass beads here in a pseudo 2D system. So this is optical imaging, but we compare it as well to our 3D imaging. A second project is a project funded by the iCubed Junior project. I'm very happy that this is a collaboration between our institute and the Institute of Multiphase Flow, led by Michael Schlüter. So Hannah Rennebaum and Felix Kexel got money from this iCubed project to look at a system both with optical high-speed imaging from different angles, so you can really reconstruct a 3D image in such a gas bubble rising in a liquid column. And our part of it is to deliver the MRI experiments. And these are the first MRI experiments of this system. So I've never shown any images that were taken by the system. So you're the very first ones, and they were taken yesterday night. So they will get much better. We still have attenuators on them because the company of the coil needs to come back next week to tune something. But at least it makes images for now, and I just wanted to take the opportunity to show it to you as well. Another collaborative project is together with Mirko Skiborowski that I also saw here. And here we look at the wetting of structured packing. So we just submitted this proposal to the German Research Foundation, and we hope to get funded. And we want to see how different packings behave under different conditions, and look at the wetting and the surface area and the flow of the liquid inside these reactors. Another project is in collaboration with Irina Smirnova and the Institute of Thermal Process Engineering. And this is also very much related to the smart reactors. We're already getting started. Here we're using a different hardware. This is on a low field system currently located at Andreas Liese's lab. So also it's collaboration with his lab. And we will get such a device, a low-field NMR system, also in our lab soon, thanks to the TUHH CRC smart reactors. So we're really happy. And that will have even higher gradients, so we will be able to see these pore structures, for example, in swelling lyogels. So I need to explain you what this is. So it's a structure inside the reactor that changes its shape, its size, when something in the input, in the material stream changes, for example, the temperature, pH, or the quality of a raw material. And for example, it expands and thereby reducing the flow, and that can be used as an actuator, a smart actuator that regulates a system. And we want to understand, for example, in lyogels and hydrogels, how, for example, solvent exchange going from something very hydrophilic to something less hydrophilic, how do the pore sizes change? And we see that these are already preliminary things, but we do see that we get increased, two different pore size distributions and increased surface interactions when we go into more hydrophobic things. All right, so this is all. We are already at the end of the time, and I really would like to take the time to show you the system as well. So I do thank you for your attention. I do thank many people. So first and foremost, my team that has been very, very supportive. It's such a joy to work with you together every day. And thanks also for your patience. So these last years have been very hard, having to deal with delays and deliveries. And also in the last half year, we had a lot of failures. So we had our first image taken in July, and then we had a cable that kind of burnt. And then we had another part from Philips that hardware of Tesla broke, and then they kindly delivered a new part of that. But that takes a lot of time, and thanks for your support and time. It's really enjoyable to work with you. And I would like to thank all the members of Hamburg University of Technology, the presidential board, that are also always very, very supportive, and I think, you have this school on the right track, and it's really nice to work in such an environment. My colleagues at the School of Process Engineering, that are also very, very nice people, and I really enjoy being part of you. My previous collaborators, my doctoral supervisor, Klaus Brüssmann, and colleagues that took all they came all the long way here, and for supporting me throughout the last years, and maybe also before, but also after I left there. The Deutsche Forschungsgemeinschaft for funding most of this, and also the city of Hamburg and Hamburg University of Technology that the city funds. Right? And last but not least, all members of Smart Reactors. I'm really looking forward to get started with you right now. All right, thank you very much. One thing before I forget, we do have beer here, and it's not any. It's a very special beer because we brewed it ourselves. It was a team event by Campus Perle. So Daniel Niehaus, he's here. Thank you very much for sharing this day with us and showing us how to brew beer. We have brewed almost 100 liters, I think, so we should have enough for today. It's a biochemical reaction par excellence. So you have enzymatic digestion of starch to sugar. You have separation, cake filtration. You do have fermentation with yeast. It's a really biochemical process, and we enjoyed it, and I hope you can enjoy the product of that. And thanks again. And if there are any questions, I'd be very happy to take them.
Thank you, Alex, for this great and inspiring lecture. It was really amazing to see what you can do with MRI. It's going to be hard now to take questions when you show the beer. So I don't know if there are any pressing questions that we should discuss. I see one here, Hossi.
I mean, in a proton resonance frequency shift-based thermometry scenario, it would be quite difficult, I would say. But I guess you could use other thermometry approaches, like, diffusion-based, where you look at diffusion coefficient that changes with temperature quite a bit as well. So I guess if you would really measure the both at the same time, I'd say, the proton resonance frequency shift approach isn't the best to go for. Mm-hmm.
Any other?
There was also a second question.
Yep.
The second question was, if you have catalysts which are metallic in the system, can you do the measurements, or is like there's a threshold for the size of the catalyst that they can be present in the reactor somewhere? You can do MRI technically.
Yeah, metals are always problematic because they eat up homogeneity, especially if they're ferromagnetic, so that's really a no-go. Metals, under some circumstances, I know my senior engineer who's sitting here, I might suggest him also as a partner to talk to during the beer, did NMR on batteries, so lithium-ion batteries in New York with Alexei Yerzhov, and that is something that you can do. It's not excluded, and also my postdoc here, Raquel Sayal, she also did MRI in the vicinity of metal objects, and there are some restrictions, but there's also some tricks you can do with orientations, and that might help you out here. If you have a packing that consists of metal catalysts, I would say MRIs, then it's gonna be tough, because if there's only some metal objects, but if they're throughout, then you have problems with penetrating with PRF. Then the signal needs to come out again as well, and so it is. We would need to look at it at any specific system, I would say.
Okay, I really saw the beer. I can't hold it any longer, so I would say we postpone all the technical discussions into what comes after. Alex, you might want to instruct us if we just storm all to the lab or form groups, or how this is going to work.
There's going to be 3 tours. One is starting in 5 minutes. The second one, so we thought it would be at 6, but now it's going to be at 6:15. It's okay. The second tour, then it's not at 6:30, but probably 6:40 or something. And the third tour then will be at 7:05, let's say. So if you decide to do the first tour, you probably end up not having as much food, but you can. It's up to you, but I think there will be more people coming right now, so I think the food is a good alternative. And there's other 2 tours. So ideally, we would have to have something like 30 people per tour. If it's more, it's mainly to show you the system in its size and where it is on campus. So there is a sign outside that says where we meet, and at these meeting points at 6:15, 6:35, and 7:05, the tours will start. All right.
Okay, then we believe in self-organization for these tours, and I would say let's give a great hand to Alex for this fantastic lecture, and welcome again.